So we have a population of black bears. We will let X here denote the number of bears at a given season T. And so that basically means that X is the number of bears after T many seasons. Okay. So the following system of bears is described by this equation right here. That's our dynamical system there. And we have that basically the bears next season are going to be 0.25 times the bears this season plus some constant C. So what this actually means is pretty interesting. It means that 75% of the bears die, right? Because if you look at the bears next season, which is xt plus 1, you only have 0.25 of the bears from last season, which means something happened to the 75% that are no longer here, right? So that's how you interpret this, is that next season there are only 25% left. That is 75% are gone. Maybe they got taken away. Maybe they died. Who knows? And we also have a plus C here. And this plus C could be, assuming if it's a positive number, if C is greater than 0, let's say C was 10, then that means that in addition to the bears that were removed, so the 75% that got taken away, for example, we could have added 10 extra bears. So even though we lose 75% of the bears we had, we added 10. And if it was negative, if C was negative, then that means we took away even more bears. But in this case, C will be positive. So let's go ahead and actually solve the questions that are asked after we got an understanding of the system. It's always good to, even if you have a system that's given to you, like the equation's given to you, it's always good to understand what it actually means. So in this case, what it means is that, again, let's assume that C is positive. It means that we lose 75% of our bears. We lose 75%, so 75% loss, but we introduce a number, a constant number C each season, okay? And again, if C were negative, then that means that we take away a constant number of bears each season. All right, what is the updating function? So our system is right over here. So the updating function, we just rewrite this, but we put X's instead. So it's 0.25 X plus C. You could also write it as fraction, so a quarter X plus C. Either is fine. All right, what is the equilibrium? Well, you should remember if your updating function is the form Rx plus D, and ours is quite literally 1/4 X plus C, okay? Then the equilibrium is automatically X star is equal to D over 1 minus R. And in this case, it'll be, well, D is C, so it's going to be C over 0.75. 1 minus R is 0.75. That's how we can write it. Another way of finding the equilibrium is you oppose the equilibrium condition, right? You feed the equilibrium into the updating function. The updating function is going to update it. But what do you get when you try to update the equilibrium? Well, you get the equilibrium because that's what the equilibrium is. It's when you put it in the updating function and the updating function gives out that same value. That's why it's an equilibrium. So if you actually go ahead and solve this, you put X star is equal to 0.25 X star plus C, and you're going to get the same thing. X star is equal to C over 0.75. All right, now we want to know if the equilibrium is stable or not. Why is it stable? And notice that we don't actually have a value of C here yet, but we can still predict the stability of the equilibrium. And the equilibrium is stable. Here's why. If we were to sketch it out, if we were to cobweb it, okay? Let me just cobweb it real quick. Pretend we were to cobweb it, really. This is going to be our axes here. This is our X. This is our f of X. Remember, we always need the line, the neutral line here. Y is equal to X. Boom, we've got that guy. And now, how do we put down our 2x or 0.25x plus c, right? Because our updating function, remember that our updating function here, f of x is 0.25, or I'll actually write it as a quarter x plus c. So the way we draw this function is we know that the y-intercept is c. Now let's just, for the sake of the argument, assume that it's positive, but you'll see that this is really valid no matter what the value of c is. And now we got to get our slope. Well, our slope, what's important to get here is that our slope is a quarter. A quarter slope is less than 1, right? So as far as slopes go, this blue line is going to be less, the yellow line is going to be less steep than the blue line, right? Because the blue line, x, has a slope of 1. So the yellow line, being less steep, is going to have a slope that is less steep. It doesn't matter how, like, less steep by how much. It just matters that when we draw it, it's still less steep. Okay, and we'll get something like this. And if you vary the value of c, you'll just raise this or lower it, whatever, but your same principle will apply to the equilibrium. And if we try to cobweb it, let's go ahead and try. Go over here, we go over here, we go over here. Oh, we make it to the equilibrium. It's stable, right? We can start further away. We can start here. Boom, 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 back to the equilibrium. We can start closer over here. Boom, 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 boom. We move our way to the equilibrium. And as a general rule, you could remember that if your updating function is of the form f of x is equal to rx plus d, and again, it doesn't matter what d is, you will always be stable. You will always be stable if the absolute value of r is less than 1. Okay? And you will be thereby unstable if the absolute value of r is bigger than 1. Okay, that's it. Because it would be steeper, right? If the absolute value was bigger than 1, then you would have something that is, say, steep like this. And if you try to actually cobweb this thing, right? So this is an arbitrary example of an unstable equilibrium. If you try to cobweb this, here's what you get. You go over here and you move to the x and you move further, right? We could even start really close to the equilibrium, like start over here. And where do we go? We go to the x, boom, 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 we move away. So this is for an unstable equilibrium. Just so you know how that looks like. But basically, this is the rule, okay? If r is, if the absolute value of r is bigger than 1, then it's unstable. If it's smaller than 1, as is our case, then it is stable. And so in this case, it is stable. Okay, part D, assume c equals 75, calculate the general solution. And we also have to get an initial value here. We'll assume it's 50 because we're given it in the next step. Okay, so we have in part D, we are given c equals 75 and x naught is equal to 50. We want to calculate the general solution. So we actually need to compute the equilibrium for real this time. And we remember that the equilibrium was c over 0.75. Okay, so we have 75 over 0.75. And this is easy to do, but I am lazy. I'm just going to use my calculator. So we get 75 divided by 0.75. It'll be 100. Okay, that's our equilibrium. And x naught is 50. So now if we go ahead and calculate our general solution, remember for a system f of x equals rx plus d, the general solution is always of the form xt is equal to r to the t times x naught minus x star plus x star. Okay, in our case, r is a quarter, x is x, and d is, in this case, d is the c, which is 75. So this is pretty easy. We get a quarter raised to the power t. X naught is 50, x star is 100, so it's minus 50 plus x star. What's x star? It's 100. And here we go. This is our equilibrium population. So you can see that it actually decreases, right? Because this is negative. So as time goes on, the graph of this would look something like that. And it would converge to 100 over here. All right. That's how this works. Okay, now we have another question. We want to cobweb 4 steps. So assume x naught equals to 50, cobweb 4 steps. Let me just move. That's the next question. X equals to 50. Let's cobweb 4 steps. Why not? So we will draw our y equals x. This is the x. This is our y equals x. X on the x-axis, f of x over here. We might as well draw our updating function properly this time. Well, at least try to do it to scale as best as we can. It's a quarter x plus 75. So let's say 75 over here is somewhere here. Our updating function, we know it's a quarter x, so it's going to be less steep. That's a crucial thing. That's a crucial thing, to make it less steep than the x. You make it more steep, you're going to get the wrong thing. You got to make it less steep. Okay, our equilibrium is over here. Our equilibrium is over here, and we know that this equilibrium is at 100. Okay, so the equilibrium is at 100, and if we cobweb 4 steps, we start from 50. We cobweb 4 steps. Here we go, and we go boom, right here, right here, right here. So sorry, this is our first step, right? This is, I guess we should have picked a bigger number or drawn it bigger, because we're not going to really get 4 steps here. But where we fall over here is this would be x1, right? Because this is x naught. So we cobweb, boom, we fall over here, we're at x1. Then we're going to cobweb again. We're going to cobweb again, and this is going to land us over here. This point right over here. If we trace that down over here, that's going to be x2. And if we did that again, we'd get x3 and x4, but we're not going to do that because we'll simply run out of space. But this is how it's done. You should know that. If you need help, watch the cobwebbing video. Okay, and then the last one, if we want an equilibrium of x star is equal to 100, how many? Okay, I wrote fish here. It should be bears. Bears, bear with me, but it's not fish, it's bears. Okay, so if we want an equilibrium population of 200, how many fish do we need? Well, this is easy. Again, your equilibrium population is we calculated over here, right? Is x star c over 0.75, right? C over 0.75. That's the equilibrium population. Okay, before we were given C, we were told to assume C is 75. Now we're actually asked to find C given an equilibrium population of 200. So we want 200 to be our equilibrium population. So C is just going to be 75% of that, right? It's going to be 0.75. If you take this equation here and multiply by 0.75, you get this. And of course, 0.75 of 200 is 150. So you'll need to add 150 bears every time to get an equilibrium population of 200, okay? And that's it for this problem.